Welcome, everyone. For today's prep, I want to look a little bit at how to kind of picture what a sequence visually looks like. And then this will lead us to limits. So we'll just get into a little bit on calculating the limit of a sequence. All right, so first, how to actually kind of visualize what a sequence looks like. And there's kind of two options that we'll consider. Plotting the sequence on the Cartesian plane, so plotting it on the xy plane. So we've got our xy plane. And let's look at this example. So we have the sequence 3 times n divided by 2n minus 1. Our index is starting at n equals 1, and then it just counts up from there by integers. So 2, 3, 4, so on. So n equals 1 is telling us what our starting index is. So essentially that's telling us the starting point of our sequence. So the very first point we would plot is the x-coordinate would be 1, our starting index value, and then we plug 1 into our formula, so a1. And then 2 would be our next x value, and then we plug 2 into our formula and get the next term in our sequence. So normally we just call that a2. And then we just keep doing this over and over and over, and we keep going. All right, so let's kind of just compare. We've got our sequence. And the general term here, the formula for our sequence, is this 3 times n divided by 2n minus 1. And the key thing here is that n is an integer. Usually it's starting at n equals 1, and then it just counts up by integers from there. Now there's kind of a natural analog to this, and that is, well, what if we just switch the n's to x's? What would that look like? So f of x. So let's just switch the n's to x's. So that would be 3x over 2x minus 1. And in this case, the x is a real number. So what's the difference between these two things? Well, when we consider a function like this with x's, this is giving us a curve. Or you can think of that curve as like a path. And when we talk about a sequence with integer inputs n, you can think of this as really steps on the path. So the sequence here is giving us discrete steps along our path. And the function is the actual curve. It's the actual path that we're traveling on. So this is one way to kind of picture a sequence, is we have this curve y equals f of x plotted in the xy plane, and then we have kind of these discrete points on our curve. Another option, another way to think of a sequence, picture a sequence. So same sequence here, but we can just picture these values on a number line. So the very first point here, so we have this number line, and you can think of this as like the output line. So these are all the output values. So maybe this is like the y-axis, if you want to think of it in terms of the xy plane. X would be the input, y would be the output here. So this is kind of like the y-axis we have. So when n is equal to 1, if we plug that into this formula, we get 3 divided by 2 minus 1, which is just 3. So this first point we plot on the number line at 3. So this would be a1. And then if we went up to the next integer, 2, plug that in, we get 6 divided by 3, which is 2. So the output there is 2. And then we just kind of keep plotting the output values on this number line. And I kind of like this picture. I like both. But I like this visualization because you start to see something, and we start to see something interesting here. And what we start to notice is that as we plot more and more of these numbers, or these steps on our number line, they start to bunch up. So what we notice here is that the terms start to bunch together. Sometimes we call this, it's like they're accumulating. So they start to, all the little points that we're plotting from our sequence, they all kind of just get bunched together at one place on our number line there. And when this happens, something interesting's happening to our sequence. And what we're going to look at is our sequence is going to have a limit. So this is one way to visualize limits, is if we plot these discrete points, they all start to bunch together at a specific place on our number line. And you can kind of see that in the Cartesian view here. If we're viewing our curve, the function as our curve, well, it looks like as we're taking these steps, it looks like we're kind of headed to a kind of a specific place along our y-axis there. All right, so how do we actually calculate the limit of a sequence? So we'll look at how to actually do this, but the definition for a limit is the limit of a sequence is a number L, such that when we make n sufficiently large positive, so when we make n big enough, the terms in our sequence become very close to this number L. So they might not ever actually be equal to L, but the terms in our sequence are getting closer and closer to this number L. And if that sequence converges, then, so if that limit exists, we say our sequence converges, and if that limit doesn't exist for whatever reason, then we say the sequence diverges. All right, so we'll talk more about this graphical representation a little bit in class, but I want to just try an example where we actually calculate one of these limits. And to help us with this, we have all of our limit laws. And all of these limit laws we saw back in Calc 1 for real variable functions. So if we had two functions, f of x and g of x, and we're adding them together and calculating the limit as x went to infinity, well, we could break it up. Do the limit of the first function, the limit of the second function, and then add the results. So the same idea is going to apply to sequences. So if we have two sequences an and bn and we try to add them together, well, we can just first calculate the limit of the terms in our first sequence, then calculate the limit in the terms of our second sequence, and then add the results together. And then same thing for subtraction, same thing for multiplication, and same thing for division. Division is the only one we got to be careful of here, and that is because, you might have division by 0, so you just got to be a little careful. So this doesn't work if you have division by 0. Kind of a usual thing. And then these are our algebraic operations: addition, subtraction, multiplication, division. We also have a rule for constant multiplication. So again, these are all things we've kind of seen before. If we have a constant multiple c that's multiplying every term in our sequence, well, we can take that constant and kind of move it out in front of the limit. The limit of a constant is the constant, and we have this power function 1. So if we have a sequence where we're raising every term in our sequence to the same power, well, we can really just look at the limit of the stuff inside that power. This one also, sometimes you got to be a little careful if your exponent is like a square root or something like that. But The main one here is this division by 0. All right, so these limit laws, these we just want to keep in mind. These are things we've seen back since Calc 1, just a slight different spin on them. All right, so how are we actually going to use those limit laws in practice? Well, one of our main results here that really allows us to use all of our old tricks and techniques from Calc 1 is this theorem here that says if we have a sequence AN and we view AN as the output of a function f, so here we're just viewing function f with just integer inputs, but this function f also allows real variable inputs, well then, if the limit of our real variable version is equal to a limit, then the limit of our sequence is equal to that same limit. All right, so it's quite a mouthful there, but let's kind of think about what this means. So we're viewing f as the formula, the function that kind of generates our sequence. We're just plugging in integer values. But the function works for real numbers in general. So when we calculate the limit of a real variable function like this, what we're doing is you want to think of this as like we're following the path. So this is, we're seeing where our path goes. Where is the path taking us? And when we calculate the limit of our sequence, what we're doing is we're looking at the steps on our path. So what this theorem says is if our function is taking us somewhere and we're walking along our path, we're walking along that curve, well then we're going to the same place. So if our function is going somewhere, if our curve is going somewhere, if our path is going somewhere, and we're taking steps along that path, well, we're going to the same place. And you can kind of see that here. So we have this graphical example that we looked at. We have the main path, and it looks like it's approaching a horizontal asymptote. And if our function is approaching that horizontal asymptote, and we're taking steps on that path, well, then we happen to be approaching that same horizontal asymptote. All right. So the one kind of important limit that we're going to really extract from this, we'll get other ones as well, is limits like this, where we have 1 over n raised to some positive integer r. So 1 over n to the r. And this is a c over infinity form, so it's equal to 0. Now, where does this come from? Well, back in Calc 1, we looked at 1 over x to the r as not n went to infinity, x went to infinity. And we saw that this was equal to 0. So if we replace x with n, well, because the real variable version is going to 0, it's getting closer and closer to 0, when we kind of abridge and just look at just integers, well, we have to go to the same place. So we're also going to 0 for just these integers. So let's try an example. We're just going to look at example 1 here, and we're going to keep this limit in mind. And we had a special technique for limits at infinity. And we're going to use this one here. So when it was real variable functions, we called it the x to the n method, or x to the, I'll say r method here, because we're using n. So how did that method work? Well, we looked at our function, and we picked out the largest power of x in the denominator. And then we just divided everything by it in our fraction. All right, so we've got 3n divided by 2n minus 1, and we're interested in where is this sequence going as n gets bigger and bigger, as n goes to infinity. So we're going to employ this Calc 1 method of picking out the largest power of n in the denominator, and then just dividing everything by it. So in this case, the largest power is just n. So we're going to multiply the numerator by 1 over n, and we'll multiply the denominator by 1 over n. So this is just our fancy one here. And then we just distribute. And just to point out, if this was like an n squared, well, then we'd be dividing by everything by n squared. So whatever the largest power in the denominator is. So when we multiply, we simplify. So in the numerator, we get 3n over n. In the denominator, we get 2n over n minus 1 over n. And then we further simplify those fractions. So the n's cancel, and we're left with the limit as n goes to infinity, 3 over 2 minus 1 over n. And what happens if we think about our limit laws, the 3 here is just a constant, so that's just going to stay constant. The 2 is just a constant, so that's going to stay constant. And this 1 over n, that's a little c over infinity form. So that's 1 over a power of n, so that's going to go to 0. So when we calculate this limit, we get 3 over 2 minus 0, which is just 3/2. All right, so we'll practice more of these limits in class, and we'll talk a little bit more about visualizing these limits and things like that. And you can probably see an example too. We're going to be able to use L'Hopital's rule in some cases. So we'll see you then. Bye-bye.